everyone. Welcome back to SAT Math Question of the Day. Here's our question of the day. Please read it, pause the video, come back, and we will do it. Now, this is from a going to be now an obsolete type of SAT. But anyway, let's get to it. Okay, trapezoid ABCD is similar to trapezoid PQRS. Okay, the length of each side of PQRS is 3 times the length of, so it's bigger. The length of the corresponding side of trapezoid ABC. The area of ABCD is 6 square centimeters. What is the area of the larger triangle, the larger shape? Teachers love this question. People who make tests love this question. When you have similar figures, the area goes up as the square of the proportionality constant. If it's 3 times bigger size-wise, lengthwise, area is 3 squared times bigger. So that's the answer. Now, this is from a non-calculator question from the October 23 written SAT test. There are no more. The future tests are going to be digital, and they're going to be calculator only. But they'll probably expect you to know this. And the volume goes as the cube of that ratio. That similarity ratio. Volume goes as the cube, area goes as the square. When you say goes as, it means you take the area of the small thing, multiply it by 3 squared. You take the volume of the small thing, you multiply it by 3 cubed. It's one of these things that's highly suggested you just know. And if you don't know it, you can't do the problem. If you do know it, maybe it takes 5-6 seconds to read the question and 3 or 4 seconds to do the problem.
Well, I can sketch. I will sketch. I can sketch how to visualize it.
Okay.
So that you don't know it. So you could go beyond knowing it in terms of explaining it in words.
Right. So that's a good background that's good to do now to go over, and that'll help you remember it. But on the SAT, you are not going to be doing what Seth's doing. You just have to know this cold. Do you agree, Seth? That for the SAT, you just have to know this.
Well, it's a matter of how it comes to your mind. It's
Right.
Yeah, I guess so. And so when a length measure changes by a ratio, the area of the similar figure changes by the square of the ratio. Yeah.
Right. So we always ask the same 3 questions. Let's just jump to the most important question. What's the essence of this question? It's pretty clear what the essence of this question is. It's exactly what Seth just said. That's the essence of this question. That's the key to this question. That's what the people who wrote this question are finding out, whether you know or not.
That the area goes up as the square of the proportion of lengths.
Exactly. So this is very, very clear, very isolated. This is what they want you to know. This is the key to the problem. Calculator? No, I mean, this is not a calculator question. This was on the non-calculator part of the older SATs, even though it's not that old. And would you do this question any different from school? No, because in school you really have to know how to do this question also, except it wouldn't be multiple choice. But Seth, you want to now give a more expound upon this concept?
Okay, yeah. So clear your blue stuff.
I'm just going to knock it. I'm going to knock everything out. And I'm just going to put over here 3 times 3 squared is. Wait a second. Did I make a mistake? It's 3 times 9.
It's 6. It's 6 times 3 squared.
It's 6 times
6 by 9.
Yeah.
It's 54.
6 times 9 is 54. Okay, got it. Now it has a lot of space to explain. So if you're not, this is a good thing to listen to, because if you see it from this perspective as opposed to just memorizing it, it'll stick better.
Okay. So let's say the original figure. Let me sketch the original figure.
Oh, it's a trapezoid.
I don't care. Okay, good. There's the original figure.
It's not a trapezoid.
And let's consider. Okay. So there's the original figure, right? And now, suppose we say make a bigger figure by multiplying the lengths by a particular factor. In this case, let's say it's 3. Let's say 3. So here's the original figure. And the new figure comes from, say, expanding the original figure 3 times.
Well, that's a clever way of thinking about
To the right.
Oh my God, I never thought of it that way.
Well, yeah, it's an education. And then we expand it 3 times vertically. Back up. Come on, back up 3 times vertically. Let's do it nice and patiently. I'm almost, well, not quite. Let's just do it. So just think about this, expanding it by the ratio, which is 3, and that expands it both in the vertical direction and the horizontal direction, right? And now this is say let's encircle let's encircle the original figure to think of the area, and then encircle the expanded figure, right?
Right.
And so the number of duplications of the original figure, well, when you expand it by 3 in the first direction, and expand it by 3 in the vertical direction, the total, sum of the areas is the original times 3 times 3.
Right.
Yeah.
I'm not sure I totally get it. I mean,
this is the intuition. This is sort of a sketch.
Intuitive approach, right? So you're basically saying if you have one thing, it gets 3. Oh, wait. If you get one thing here, it gets 3 expanded by 3 here, and also 3 up.
Yeah.
So in other words, you got 3.
Yeah.
We've got it 3 times bigger in this direction. Oh, and then you also have
and 3 times bigger in the vertical direction.
But when you
the idea is conveyed by the picture.
So what about perimeter? But perimeter
is a mesh. The perimeter is a length measure.
Right.
The perimeter for the perimeter is proportional to the length of one side for similar figures.
So then why isn't it 9 times, playing devil's advocate, using this little picture? Why isn't the perimeter 9 times? 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3. Why isn't the perimeter 9 times?
The perimeter, the area is the thing covered by these circles.
Right.
That is different from the perimeter. The perimeter is what you drew. It's this box. It goes like this.
Oh, that is 3 times bigger.
This is the perimeter. It goes around it. The perimeter of the original is this.
I see.
And so what we have is this part of the perimeter, say A, goes into A plus A plus A, 3A.
Right.
This part of the perimeter, B, goes into 3 B's, B, B, B. this part of the perimeter goes into three C's, C, 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 and this part of the perimeter goes into three D's, D, D, D.
So if we change the problem to say the length of the side of the trapezoid is, well, let's do a square. The length of the side of a square is 6.
Yeah.
I'm changing the problem, okay? Everyone, excuse me. So if the length of the side is 6 and it goes up 3 times, then the perimeter is originally 36 times 3, which is like 108 or something.
Yeah.
Now let's see, that means 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Wait.
Yeah.
12 times 6 is only 72. Oh, wait, but the original perimeter... Original perimeter was 36. Okay, because it's... 4. If it's 36, it's 4. 4, 4, 4. If the original perimeter of this thing... Well, I'm getting so confused. It's 6. 6 times 4 is 24. Sorry. If you have a square, original side is 6. 6 times 4 is 24. So, and it goes up by 3. So 24 times 3 is 72. And that's 6. That's just laughing. So that's 6, 6, 6, 6, 6, 6, 6, 6, 6, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 72. Right. Okay. Got it. So it works for perimeter.
Yeah. Now, let me, how about, maybe remove all, could you clear the drawing?
I am. I'm going to take away all my garbage.
Can you take away my garbage too?
Really? Everything? Wipe it clean?
Yeah.
Okay, you asked for it. Okay. But
now, a rigorous argument is as follows. Let me give a rating. Okay.
I just want to keep the answer.
The rigorous, the principle is, what is the area of an arbitrary figure, right?
Okay.
The area is the total area. The area is in the limit, the total area of filling the figure with little squares.
Okay.
Okay?
Right.
Now, if you expand the figure by a given ratio, the little squares will expand in length by the same ratio.
Right.
And so to see how the area expands, what we need to do is analyze how a very particular figure expands in area, a square.
Yeah, we just did that.
No, we didn't. What I did was use a glob.
Okay.
So let's consider an actual square.
Got it.
A genuine square.
Got it.
Right?
Got it.
Whose and the length of the width of the square, let's say is it's called A, right?
Okay.
If you expand by 3,
yeah,
what you get is a square. One.
Yeah, a side of 3A.
A square, yes, whose sides are 3 times A.
Right.
And then the area of the original square is A squared. When it's multiplied by, when it's expanded, the area of the expanded square is, the side of the length of the side squared, which is 3 squared times a squared.
Right.
And so the area of the little square goes up to the original area of the little square times the square of 3, or 3 is the ratio. And of course, we could generalize this. We could generalize this by taking instead of 3, replace 3 by R.
R for ratio. R for ratio, right. Yeah.
Yeah, so you could take, so then the 3 becomes an R. This becomes RA, and RA squared is equal to R squared times A squared. So A squared goes up to R squared times A squared. But the point is, this argument is only true for squares.
Right.
But it applies to any other figure because the area of any other figure is the limit of the areas of the squares, of tinier and tinier squares that fill the figure.
Right, and we know that about anyone who looks at a computer screen, which are called pixels. Pixels are the tiny little squares of each color in our screen. Tiny little squares. And every shape, like you watch TV, you watch us, God forbid. You do anything, all the shapes are made out of just tiny little squares called pixels.
Yeah. Now, then the same argument applies to volume, except that instead, in the place of filling a figure with squares, and then you're doing it with smaller and smaller squares to get the area. To volume, you fill the thing with cubes.
Right, and then the volume of a cube is the cube of each side of a square. Right, so it'll be R.
The volume of a cube of length of where side is A, the volume of that cube. The cube of whose side is A, the volume is A cubed.
Right, and RA, if the side is RA, or ratio times A, will be R cubed, A cubed.
Now, the reason...
So let's move on, okay?
The reason, at least for an integer, why this rule is true is that the reason why it's true is that the 3 by 3 square is composed of... It's composed of 3 times 3, 9 little squares.
Right. Okay, we're more than done. Done. Now, everyone, if you've gone this far, and you've figured and you've followed us, now this can now stick a little deeper, because now you have a better understanding as to why this thing is true that they tell you in school. They basically force you to memorize. Okay, or force you to understand. Okay, so...
If they do it all.
What?
If they do it all.
If they do it all. Okay, fine. We're done with this question. So now let's introduce ourselves quickly, say goodbye to everyone so everyone can move on their day. I'm Joel. I have a PhD in mechanical engineering from Columbia University. My brother Seth has a PhD in math from MIT. You could tell how he explains things like this. He's been a professor in computer science in SUNY Albany for many years, and now he's retired. So we meet each day to go over SAT math questions, give you a perspective, give you advice on how to do them. We try to look at them from different perspectives, give you some understanding, and hopefully you're picking something up from our question of the day. In terms of studying, do as many practice questions as you can, but particularly focus on the ones that focus on the topics you're a little weaker on. Take tests, figure out which questions, which sections of the test you're not sure about. Practice on those. Go to Khan Academy. They have hundreds of practice questions, and just work on practice tests and learn from your mistakes.
Yeah, and practice means try to do the problem all by yourself.
Yeah.
Do not practice does not mean looking at the answer right after reading the problem.
Right.
And it does not mean like going to Khan Academy and sort of making just any choice of an answer and then simply reading the explanation.
Right.
Practicing means that you work on it and try to get the answer as if you're taking the test.
Right.
And then discover how that will enable you to discover what you really know and what you really don't know.
That's right.
And then the explanations can, you will find out what to get from the explanations.
Right. Yeah. In fact, it's a good thing to get, when you're practicing, it's a good thing to get questions wrong because it gives you the opportunity to learn something and get better.
Yes. If you get all the questions right, that means if you get all the questions right and you anticipate and fully understand the explanations, that means it's time to work, to study, and go into more difficult questions.
Right. Okay, we're done. We gotta go. Okay, we've been here long enough. Okay, everyone. So, please give us comments on our videos. Please dislike our videos. Well, comments are strongly encouraged. It really helps us. And if you have any SAT math questions, please email them to us at satmathquestionoftheday@gmail.com. Tomorrow's Thursday, which means Throwback Thursday. We go back 20 years to when the test had a whole different feel. Or most of the test had a different feel, and we will play with one of those questions tomorrow, as well as with a modern question. Okay, everyone, have a great day. Bye-bye.